This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some of the relevant concepts associated with the released free response question AB2 from the 2021 AP Calculus exam. My name is Steve Kokoska. I'm a professor emeritus at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. The free response portion of the AP Calculus exam almost always contains a problem that involves particle motion. And although students and teachers have become accustomed to these types of questions, there are still a few concepts that I'd like to emphasize in this video. Let's suppose a particle moves along a horizontal line such that the velocity of the particle is given by v of t. First, I'll review the technique for finding the position of the particle at time t. Then we'll consider the difference between displacement and total distance traveled, and how we might visualize these values. And finally, I'll try a few examples. Note that often these AP Calculus exam questions are on the calculator active portion of the exam. So I've designed my examples to be calculator active. First, let's review these important concepts. The fundamental theorem of calculus part 2 says that if f is continuous on an interval a to b, and capital F is an antiderivative of little f, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Now, if capital F is an antiderivative of little f, then we can write, of course, capital F prime equals little f. So we can rewrite the conclusion of the fundamental theorem of calculus in this way. Many instructors and many textbooks call this more general equation the net change theorem. Students learn that capital F prime of x represents the rate of change of y equal f of x with respect to x, and capital F of b minus capital F of a is the change in y as x changes from a to b. But we need to remember that y could, for example, increase, then decrease, and then increase again. And therefore, capital F of b minus capital F of a really represents the net change in y. Here's a closer look at this important concept, the net change theorem. Here's another, more general way to think about this important definite integral. This represents an accumulation of the change in capital F over the interval a to b. And there are just loads of AP Calculus exam questions involving this concept. If we rearrange the terms in the net change theorem, we get an alternate, very useful interpretation and a practical approach for solving many problems, particularly particle motion problems. This says that the end amount, or for example where the particle ends up, is equal to the start amount, or where the particle started out, plus the net change, or the net distance traveled. This principle, again, has all kinds of applications, and we've seen many on the AP Calculus exam. For example, we've seen water flowing over a dam or in a pipe. We've seen the accumulation of snow. And we've even seen people entering and leaving an amusement park, as well as some of the other applications listed here. Let's discuss this net change theorem in action, applied to particle motion problems. Suppose a particle moves along a horizontal line so that its position at time t is given by s of t, and therefore its velocity at time t is given by v of t, which is equal to s prime of t. First, if the position of the particle at time t equal t sub 1 is s sub 1, then we can find the position of the particle at time t equal t sub 2 using the net change theorem. The position at time t sub 2 is simply the position at time t sub 1 plus the net change. The net change in the position of the particle, or the displacement of the particle, over the time period from t sub 1 to t sub 2, is given by this definite integral. Now, note that there is no absolute value symbol here. This accounts for the particle moving in both the positive and the negative directions. And finally, if we want the total distance traveled by the particle over a time interval, then theoretically we need to consider separately the intervals where v of t is greater than or equal to 0, that is, where the particle is moving to the right, and the intervals where v of t is less than or equal to 0, where the particle is moving to the left. However, we can simplify the process if we consider the absolute value of the velocity function. Therefore, the total distance traveled is given by this integral expression. We can certainly interpret displacement and total distance traveled as areas under a velocity curve. And I know you've seen these illustrations before, and I'll show you one more in the context of an example. But I'm also going to show you another visualization of these ideas. First, let's consider a visualization of the net change in position or the displacement of a particle over the time interval t sub 1 to t sub 2. The particle is moving back and forth along a straight line, along the position axis that I'll call S. Now, I've sort of extracted the changes in and the directed horizontal motion along the vertical axis to make it easier to visualize the motion of the particle and to understand displacement and total distance traveled. So in this example, the particle starts at time t sub 1 and position s sub 1. It moves to the right for a while and then to the left, back to the right, and then to the left again, ending at position s sub 2. The difference between s sub 2 and s sub 1 is this definite integral, the net change in position, assigned distance. In this visualization, the displacement would be a positive value, and that's because s sub 2 is greater than s sub 1. The particle ended up to the right of its starting position. And we can also use this diagram to visualize the net change theorem. The final position is equal to the initial position plus the net change in position. Here is a visualization of the total distance traveled by the particle. Starting with the same sort of diagram as on the previous page, I need to measure all of the distances d sub 1 through d sub 4. These are separate distances traveled to the right and to the left. And the total distance traveled is simply the sum of these distances, a non-negative value. All right, let's put all of these ideas together, solve a problem or two, and use some technology along the way. In this example, a particle moves along a horizontal line with velocity function v. We need to find the displacement of the particle over a certain time period and the total distance traveled by the particle over the same time period. The displacement of the particle is the difference between where it started and where it ended up. In this example, that's s of 6 minus s of 1, which is the definite integral from 1 to 6 of v of t dt. Now, this is a straightforward application of the net change theorem, or of course another way to look at this, the fundamental theorem of calculus. Now, we might try to find a symbolic antiderivative of v, but as is typical in these calculator active problems, it's just not possible. So we turn to technology for a solution, and I'll show you how I arrived at this answer in a moment. The particle's net change in position over the time interval 1 to 6 is 2.675 meters, and it's to the right since this value is positive. I I'm going to use a TI-Nspire CAS calculator to solve these problems. On this calculator screen, I defined the function v, and then I simply evaluated the definite integral. The displacement is 2.675 meters. On this screen, I graphed the function v over the interval 1 to 10. Remember, the definite integral can be interpreted as the net area bounded by the graph of v and the horizontal axis. And this allows us one way to visualize the displacement. Returning for a moment to one of my initial diagrams to illustrate particle motion. This particle starts at a position just to the right of 0. It travels to the right for a while, then to the left, and then back to the right. Again, each change in direction is illustrated by a step on the vertical axis, and the directed motion is also indicated. And this is just to make the motion of the particle clearer. The displacement of the particle is s of 6 minus s of 1, as illustrated in the diagram. To find the total distance traveled, we need to find a definite integral of v of t. Now, again, if we were to solve this problem analytically, we'd have to find the intervals on which v is positive and those on which v is negative. And then we'd have to split the integral into appropriate parts, use the definition of the absolute value function, and then find an antiderivative. And finally, use the fundamental theorem of calculus part 2 to evaluate. In this calculator active problem, we can simply write the mathematical expression that we need to evaluate, and then use technology to find the total distance traveled is 11.953 meters. Here's how I found this value using the TI-Nspire. Now remember, I already have the function v defined in this problem. And here's a visualization of this value, the area under the graph of the absolute value of v from t equal 1 to t equals 6. I found the same answer on the graph screen here, thank goodness. Here's another way to visualize the total distance traveled based on my initial diagram of particle motion. I need to add the lengths of each leg of this journey, where a leg is motion restricted to one direction. Now, I'm kind of lucky here because the particle started by moving to the right. So I take the next leg of the journey and add it to the first part, and then the third leg of the journey and add it to the total trip. So the total distance traveled is the length of this segment, represented by this definite integral, 11.925 meters. Now here's another way to think about this value, and I think a nice connection to particle motion in 2 dimensions. You can sort of picture placing a string along the particle's path, picking up the string and pulling it tight, and then finally measuring its length. Well, that's arc length, okay, in 1 dimension. By looking at this definite integral, can you see the connection to the formula for distance traveled in 2 dimensions? Let's try one more particle motion problem in which technology is required. Here we have a particle moving along a horizontal line with velocity function given. And looking ahead, I don't think I'm going to be able to find a symbolic antiderivative for v. We know the position of the particle at time t equals 0. We need to find the general position function and the position at time t equals 4. Then we need to find the first time the speed of the particle is 5, and finally all the times in the interval 0 to 10 at which the particle changes direction. We can find the general position of the particle at time t by using the net change theorem. S of t is the starting position, s of 0, plus the net change or displacement. To find the position of the particle at time t equal 4, we simply evaluate this function, okay, with a little help from technology. The position of the particle at time t equal 4 is 3.512. And here's how I found this using the TI-Nspire. And this is yet another way to visualize this solution. On this screen, I've graphed both v and s, the position function. And I simply found the point on the graph of s corresponding to time t equal 4. Although I won't go into it here, there's certainly a lot to discuss about the relationship between these two graphs. For example, what is the graph of v like when s is increasing or decreasing? This next question about speed is very interesting. Remember that the speed of the particle at time t is the absolute value of the velocity. So in general, we need to solve the expression the absolute value of v of t is equal to 5. And in this problem, we need to take the minimum value of t. I can't solve this problem analytically, so here's what I'm going to do. I'll graph v and the two horizontal lines at 5 and minus 5. And then I'll find the first point of intersection. The graph suggests that there are several points of intersection. But the first place v intersects either of these horizontal lines is at t equal to 4.952. Now, I can also find this value on a calculator screen, and this is a cool application. I can use either the solve function or the zeros function. The advantage to the zeros function is that the solutions can be stored in a list and explicitly referred to. This is really useful if we need to use a more precise value of t in another calculation. So the first time the speed of the particle is 5 is t equal 4.952 seconds. And this occurs when the particle is moving to the left. And finally, we need to find all the times in the interval 0 to 10 at which the particle changes direction. Now, analytically, I need to find all the critical values and check whether the sign of v changes at those values. I'll use technology to find these values. Here is a graph of v, and there are three values where v is 0 and the sign of v changes. And I found these three values on the graph screen. And let me leave you with a question or two associated with this part. I wonder if you can find these values using a numeric solver, let's say on the TI-Nspire or the TI-84. And can you actually find analytic or symbolic expressions for these values of t? I hope this video provides a nice summary of some important concepts associated with particle motion problems, a few AP Calculus type problems, and some examples of the use of technology to solve and visualize these types of questions. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.